let's do an example of heat transfer. So we'll have a substance that undergoes a phase change and heat's transferred to or from an object. So one way we can model this is, say we have a metal block and we're going to condense a liquid on the metal block. So it's like the formation of dew outside when it gets cooler in the summer. So we're going to have a liquid, say water, forming dew on the surface of the metal block. And we want to know the final temperature of the metal after we form dew on the block. So let's say the initial temperature of the metal is 25 degrees and the mass of the metal is 100 grams. Its specific heat is, say, 0.15 joules per gram degree centigrade, and we are going to condense 0.01 moles of water. On the outside of the metal block. So we'll have Q for the water and Q for the metal. Now one's going to lose heat and one's going to gain heat. So we need to designate that by signs. So we need to show the direction of heat flow. So when water goes from the gas to the liquid phase, that's condensation. So when water condensates, it releases heat because this is just the opposite of liquid going to gas. That's called vaporization. And the enthalpy of vaporization for water is 44,000 joules per mole. So it takes this much heat to vaporize water, so this much heat is going to be released when we condense water, go the opposite direction. So water will be giving up heat, releasing heat. So we'll use a negative sign showing that water is releasing heat, and the heat will be gained by the metal. So we use the plus sign for the metal. Okay, so now we just need to put in our expressions for heat. So for the water's undergoing a phase change. And so Q for a phase change is just the enthalpy of the phase change. So this is condensation. So we have heat lost by the water is negative delta H condensation, or negative of the negative delta H vaporization. So negative enthalpy vaporization is enthalpy of condensation. So now we have these two negative signs here. And this is going to be equal to Q for the metal. So Q for the metal is the mass of the metal, the specific heat of the metal, and the temperature change for the metal. I'll use M for metal. So now we can plug numbers into this. Okay, so now we're going to solve for delta T of the metal. So delta T of the metal is going to be equal to the negative enthalpy of vaporization divided by the mass of the metal and specific heat of the metal. Okay, so now I'll erase this so I'll have room. So delta T for the metal is equal to, so I'll have enthalpy of vaporization is 44,000 joules per mole. So I have a negative and then a negative, so that's still positive. So I have 44,000 joules per mole. And I have 0.1 moles of water, so I need to multiply by the amount of water, so moles will cancel. This will tell me exactly how much heat is released for 0.1 moles of water condensing. Now divide this by the mass of the metal, 100 grams, and the specific heat of the metal, 0.15 joules per gram degrees centigrade. And you'll see that grams cancels, joules cancels, and the only unit I will have is degrees centigrade for the temperature change. So this is 29 degrees centigrade for the temperature change, and delta T is positive, so my T final would be T initial plus delta T. So T final is equal to 54 degrees centigrade.